our first question. Right. Some of you might remember the question that went something like this. There was a river. So here is the river. And there was a person over here, call it A. And there was a guy over here called B. And there's another place here. Let's call it C, and then another one down here called D. Now, essentially in this story, a person is on one side of the river and they want to get to this point, D. And they can choose different pathways. And our job is to try and find out which pathway would be the quickest. And you're told things like the speed at which someone can row. And you're also told the speed in which someone can run. Also, you're told that this here is, well, it can be any number you like. So let's do it in metric. So let's suppose that this is 500 meters wide. And that you can, when you're in the water, you can row at 5 meters a second. And when you run, you can run, I don't know, say 3 meters per second. Now, if you change the width of the river, if you change this speed, and if you change Anders change this speed, the solution changes every single time. So there are some situations where the quickest is just to go from A straight to D. I guess I'll make that D now. A straight to D. In some questions, it's fastest to swim the shortest distance, then run a lot. And in other situations, it's a compromise between those two extremes, where there's some point C that you would row to, and then you'd run the rest. And so our quest is to find out where this C is. So if C ends up being here, that means sail across and run the whole distance. If C ends up down here, then it means go straight to here. Right? Now, how are we measuring C? We're going to measure it by calling it the distance from B. So there's going to be my X. And I'm going to add in a few extra things. I'm going to add in an invisible dotted line here and another invisible dotted line here to make a right angle. So the optimization function in this case is the time. Let's see what that is. The time is going to be made up of two pieces. The time it takes to go from A to C, plus the time it takes to go from C to D. Does that make sense? That time plus that time is the total time, right? Now, I need both these to be in terms of X, but let's break them down. If you want to do the time from A to C, it's the distance A to C dividing by the speed that you can row at. Now, I've made this person row at a really fast rate, so maybe he's got a speed, an engine at the back, but that's just my choices. And then C to D is going to be divided by 3. We'll call time T. So my goal is to find out what AC is, the distance from A to C in terms of X, and the distance CD in terms of X. One of them is pretty easy to do, and that's the CD one. Oh, and I needed to tell you another number that just came to me. You need to know this distance, right? This distance here. And let's say that this distance here is 2,500 meters, right? If this distance here is X, then C to D is what's left from that 2,500. Right? So that's going to be 2,500 take away x. Are you comfortable with that? By the way, this guy must be bionic, because to run 3 meters a second is pretty bad, really. I mean, you know, the people who do the 100 meters can run about 10 meters per second. So this guy is definitely out of shape. And the fact that he can row faster than he can run either means he's got really strong arms or he's cheating and he's got a motorboat. But back to our story. CD is 2,500 take away x divided by 3. Now, the only other distance that I don't know yet is AC, right? This guy. I know it's going to be over 5, but I don't know what AC is. And if you focus on that right angle triangle, you know this distance is 500. You know this distance is x, and you're trying to find A to C. Do you see it's a right angle triangle? And so Pythagoras is going to be our go-to guy. And Pythagoras says that AC squared is 500 squared plus x squared. So AC must be that huge number plus x squared. So we now have everything that we need. Rather ugly numbers, really quite big. That is the optimization function. Any questions so far? Are we cool? So what do we do once we get it? Well, the good thing about every one of these optimization questions is that once you've found this thing, the last 2 steps are always the same. First thing, differentiate it. Second thing, find the critical numbers by finding when x is 0, because that's going to be your solution. So I'm going to take this over on a new piece of paper, and I'm going to rewrite t in a form that's going to make differentiation easier. So I'm going to call it 1/5 round divided by 5, 250,000 plus x squared to power a half. And I'm going to call this thing 2,500 over 3, take away 1/3 x. It just makes things easier to differentiate. So let's find its derivative. Power rule, multiply by the power, and then reduce the power by 1. Times the derivative of the inside function, which is 2x. Differentiate a number, it's gone. Differentiate that guy, you get 1/3. So what do we have next? Well, that times that cancels partially, and you're going to have 1/5. You're going to have an x, and you're going to have this ugly guy. Take away 1/3. I'm going to make this guy look a little bit prettier, having the x on the top, moving this downstairs and calling it square root. It's not a surprise that the derivative is just ugly, but we do know what we're trying to find. We're trying to find when is it 0, right? Where do you think I'm going to go next? How do you think I'm going to solve this equation?
Cross multiply.
Oh, you're going to go for the algebra. You know, eventually this one would work, but I'm not going to do that. It's not that that's a bad idea. It is okay. Eventually you could get it to work. But since I'm only interested in the answer, you know, to like a decimal place, right, then I could probably just do it using what instead?
Decimals.
Yeah. If the equation is relatively straightforward, we would expect you know, to solve it in, you know, algebraic. So what we're going to do is I'm going to do y equals x divided by 5. I think you can do it square root. You can get 25, 1, 2, 3 plus x squared, which is this guy, and could take away a third. And interesting, but not what I was expecting, but that is okay. There we go. There is no solution to that puzzle. Right. And by that, I mean there isn't an optimal value for x. Well, technically there is. What value of x do you use if you can't find a critical number? Where would you sail or run or whatever you want to call it to get from A to D in this story? So this isn't math. This is just basically looking at it and saying, okay, there is no place between here and here, right? There's no value of x that's going to do it between here and here. So the shortest distance would be to go straight to here. Are you okay with that? So our solution is make x 2,500 meters. In other words, row all the way. Now, I could have played about with this number and that number. For instance, if I made this guy superhuman and he could run 10 meters a second, and I made him really slow at rowing, and I made this 1 meter a second, I could have changed the solution and have it so that he would be best to row this way and run all that way. And if I tweaked it a little bit differently, I could even make it where any point between here and here would work. Our solution just happens to be he runs really slowly and he rows really fast. And so the shortest time is going like this. A little bit unsatisfying, but when you make a question up, you're never sure what you're going to get. But the process is exactly it. You get to here, right, and you solve. And if it's ugly, you do it in Desmos. And if you can't find an answer, it's because technically you don't have a problem. Just row all the way. Right. So there's nothing to solve because none of these numbers would be any better. So our next question on my list is going to be the 4 pens question. Okay, got it. Which is something like this. This is from the test, online test 10. And the 4 pens question looks something like this. Consider a following problem. A farmer has 750 feet of fencing. Okay, so I'll write that down. He has 700 in my question feet. He wants to enclose a large rectangular area and then divide it into 4 pence. So there's a large rectangular area. I'm going to call this distance X. And I'm going to call this distance Y. And of course, you could switch places if you wanted. And I'm going to divide it into 4 pence. And I've decided to split it this way. Could I split it the other way? Yes, and you get the same answer, so we're good. And we want to maximize the area of the pen. Okay, well, the area is very easy to calculate. It's X times Y. But I need to figure out a way of getting Y in terms of X. So if I look at this badly drawn picture, the fencing will be equal to 1, 2 X's plus 1, 2, 3, 4, 5 Y's, at least in my orientation. And we know that that is 750 feet. And now I solve for Y. So I will take away 2x from both sides. And then I will divide everybody by 5. 5 goes into that guy 150 times. Take away 2/5 x. And now we know what Y is. So A is now X times Y, which is 150. Take away 2/5 x. And this gives me 150x. Take away 2/5 x squared. There's our optimization function. All we need to do now is differentiate it and find the critical numbers. If you differentiate it, you get 150, take away 4/5 x. If you make it 0, you can solve in the usual way by subtracting 150 from both sides. And, well, it really doesn't matter how you do this one. So I'm just going to write it down like this because the calculator is going to do it anyway. I'm just going to divide both sides by 4/5 and let the calculator figure it out. So negative 150 divided by negative 4/5. And the answer I'm looking at is that fella, 187.5 feet. So that's how wide you make it. And I need to know what Y is going to be. So put a little bubble around that guy. Y is going to be this fella. So it's 150. Take away 2/5 of whatever X is. So it's 150. Take away 2/5 of that number. And that gets me 150. Take away 2/5 times 187.5. And the answer I get here is 75. And then I want to squeeze everything into this one piece of paper. The best, biggest rectangle, the maximum area, is just X times Y, which means that guy times that guy. So 75 times 187.5 gets me really ugly numbers, 14,062.5 square feet. Pretty much your question, Carter?
It wasn't my question.
Wasn't Carter? Who was it then?
It was me.
Oh, how did it go? Is that kind of the way you tackled it?
Yeah, it's essentially just it.
Right. Did you split it horizontally instead of vertically?
Um,
Doesn't matter for the question, it's the same answer.
what do you mean by split horizontally versus
Well,
vertically?
so you did your pens like this.
Oh no, yeah, I did it the way you did it. Yeah.
If you decided to split the pen this way, do you know you'd still get the same answer? The math wouldn't want. It might look a different size pen, but the area would be exactly the same.
Yeah.
So there's a lot of versatility in that. Okay, who wants to jump in then with the next question? We'll try and be democratic, give everybody a shout. Because they may only be here for that one question, then they're out of here. So what you got next? Who is it? Anyone?
Can we try the volume of a spherical balloon? I think this is rate of change.
Rate of change, gotcha. So in these types of stories, you basically have a sphere that could be increasing or decreasing. I'm going to have it increasing. And you're told that the radius is increasing. Let's say whatever the units are. So when they tell you the radius is increasing, they're actually telling you the value of the derivative dr by dt. And let's suppose that it's increasing at the rate of 5 centimeters per second. And in that version, you're being asked what is the rate of increase of the volume. And you're typically told a particular snapshot, let's say, when r is 10 centimeters. Now, there's a slightly different version of the same question that would go something like this. The volume is increasing at a certain number. So if they say the volume is increasing, they've just told you dv by dt, and you're being asked to find the rate of increase of radius. And since they're both pretty similar, I'll do them. So this is the first version. You're going to begin by the formula for the volume of a sphere. Would probably, if I did that, I would tell you, yeah, the volume of whatever it is this guy. Now, you differentiate with respect to t. And if you differentiate this guy with respect to t, you basically differentiate it with respect to r, and then you do the derivative of r with respect to t. That's why it's a related rate. And so what you get is 4 pi r squared times dr by dt. And that line is going to be the same no matter what situation, which version of the situation you deal with. Now, at this point, what we then do is we plug in what we know and we find out what we don't know. Well, I don't know the rate at which the volume is increasing, because that's what they're asking me. I know that the radius is 10. And I know that the rate of change of this is 5. And so this is pretty straightforward on then. 100 times 20 gives me 2000. And so the answer is 2000 pi. Now, very similar sounding question, but with one big difference. We'll tell you that the volume is increasing or decreasing, Now, if it's decreasing, it just means the thing's negative, right? That's the only difference. So if the volume is increasing, so they basically tell me what that is at the rate, well, let's say 60 cubic centimeters per second. What is the rate of increase, or the rate, at which the radius is increasing? When, let's make that 10 again. I'll show you, when you see them side by side, how similar they are. You start with your connecting formula. You differentiate with respect to t, which ends up being that guy. You know the volume is 60, the rate change of the volume. You've got 4 pi, you know the radius is 10, and now you have dr by dt. So this is 60, and this is 400 pi dr by dt. So what do I do to both sides to find the rate of change of radius this time? How do I go from here to here?
Divide by the 400 pi.
And it's okay that that's a weird answer, which it is. The only thing I suggest you do is divide and make that 3/20 just because it looks prettier. In other words, simplify the fraction. But that's all I would do. So although these are both volumes of spheres changing through time, can you see the method is very, very similar, even if one is finding the rate of change of volume and the other was finding the rate of change of the radius with time. Are we good? Any more questions?
Can we do like one implicit function?
Sure, implicit. Let's do an x cubed plus an x squared y plus 7x equals 10. And the implicit question would be to find the derivative dy by dx. Right. Now, each piece gets differentiated, and it depends what it is, how you would approach the answer. All of these are going to be differentiated with respect to x. This guy is simply just a power rule. The derivative of the number 10 is 0, and the derivative of 7x is just 7, right? Nothing too strange going on. But the derivative of x squared, actually, let's make that y cubed, of x squared y cubed. Now that's a bit sneaky, because that's actually a product rule. And this guy is f, and this guy here is g. So let's see what we get. We get 3x squared, product rule, plus 7 equals 0. If you differentiate x squared, you get 2x and you leave the other guy alone. You leave this guy alone, and now we get to the crux of it. When you do implicit differentiation, you can differentiate functions of y, right? Sine y, e to the y, in this case y cubed, and you will get 3y squared times one extra piece. What do you get when you differentiate anything with a y in it in implicit differentiation?
dy over dx.
You get a dy over a dx. Now, from this point onwards, it's purely, as long as you do it to both sides, it's okay rule. And our goal here is to eventually just have dy by dx on its own. So we are looking at finding dy by dx on its own. So tell me some things to do to both sides that's going to get closer to there.
Minus with the x squared 3y squared.
Oh, this guy? Oh, not yet. No, not yet. How about getting, same kind of idea, but doing it with different things. How about subtracting 3x squared? Now you may say, well, why can't I subtract that? Well, for starters, isn't that being multiplied next to the dy by dx? And secondly, aren't there a whole load of other things that should go away before we even worry about what to do with that, right?
I was just gonna minus that, then divide by the x squared 3y squared.
That's exactly what you will be doing. So if I may have misheard what you said, and I thought you said take that away. So if you didn't say that, then you were quite correct. Would that be your first part of your process? Was that what you were going to do?
Yeah, I was just gonna do it on the other side basically.
Okay, then you were fine. I misheard. Right. So just like you said, then you would divide everybody. And occasionally you can do a bit of tidying up, you know, pull out a common factor, cancel, stuff like that. But in this case, this question, that's an ugly answer and it's finished. Are we good?
Yeah.
Right. Now, this question's not going to lend itself to that, but do you know you get things like what's the equation of the tangent line at the point 1, 2 or something? Then wouldn't you put x as 1 and y in 2, and that would get you the derivative value, which is the slope of the line. Then y minus y1 equals mx minus x1 would get you the equation of a tangent line. So you could have got a tangent line out of this, but that one, it'd be hard for me to figure out a point where these would come out as nice whole numbers to give you that question. But if you pretend that 1, 2 was on that curve, x is 1, y is 2, you do a whole calculation here, and I know you get -7/9, and then you could do the y minus y1. Okay, hi Vanessa, you've joined us, I see.
Yes, I have joined the awesome.
Oh yeah, well, we are the awesome team here. I totally agree with that. So has anybody in our awesome team got an awesome question to go with us? Nothing?
If no one else has one, I had one.
Mhm.
It was for optimization. It
Oh.
had a triangle and then like a line through it.
I know the one you're talking about.
Yeah, I'm not sure.
Right. So this, although we did one in class very quickly, this is also from test 10, and it's question 5. And we've got a guy here. I believe you've got a guy here. Got a guy here. Get another guy over here. An old dotted line, and another guy here. And finally, another dotted line going along the way. I'm assuming that's the one you're talking about, Vanessa.
Yes, that is the one.
That is one, right? So you basically got a town A, a town B, and a town C, and these 3 blue lines are cables. They could be roads, they could be sewage pipes, it could be oil, whatever it is, doesn't really matter. we are trying to figure out a place to put this P so that the total distance, right, is a minimum, right? So we're finding the shortest distance. So I'll call them cable because I believe in this story, this is a cable, that's a cable, and that's a cable. So we want to know what's the shortest cable. Now they do give us other numbers that we will be using. So for instance, the distance from A all the way down here, in my version is 7 miles. This distance from here to here is 3 miles. And this distance from here to here is 4 miles. And we are going to make that distance, because we don't know what it is, we're going to make that X. And so we are going to create the cable one. So I'm going to call it C for cable. And the cable is made up of 3 pieces. A piece called AP, one called PB, and one called PC. Now the piece of cable called AP, that distance is X. Now I need to know what that distance is in terms of X and what this distance is in terms of X. And so if I move this guy over here a little bit, let's focus on getting that distance PB. So I know it's a right angle triangle. I know this is 3, this is B, this is P, there's my little right angle. If you call that D, I know that distance in terms of X. That distance there, right? This one here, is that distance there. Isn't the top to the bottom 7? Isn't this piece X? So what's this distance going to be if the whole thing is 7 and the top bit's X?
7 minus X.
That means then, can't I use Pythagoras to get BP? BP squared is going to be 3 squared plus 7 take away X squared. So it's going to be 9 plus 49 take away 14x add X squared. I fold that out. And so I'm going to get 58 take away 14x plus X squared. And so BP is the square root of all of that, and I like X squareds first, so I'm putting them that way around. Right, we got it. This guy is the square root of X squared, oops, take away 14x, add 58. Now, if you want to get PC, you're going to have a guy that looks just like this. It's going to be 7 minus X this time. And this guy here is 4. And that's P, and that's D, and that's C. And if you find PC, CP, if you want to call it that, it'll end up being this guy. It's going to be an X squared again. It's going to be a negative 14x again. The numbers are going to be a little bit different. It's going to be 49 and 16. So that's 49 and 16. 65. Can you imagine I did the same thing and got that? So it's X squared, take away that one, plus 65. And we have what we call in these situations the optimization function. And we will finish it the same way we did the others today. You're going to differentiate it and find out when it's 0. And if it looks nice, we could solve it algebraically. I doubt very much if this is going to look nice. So we are going to use Desmos instead. But before I get to the differentiation, I'm going to have to rewrite it as fractional powers so I can do that. So here we go. Its derivative is 1. Multiply by the power and reduce it by 1. Times the derivative of the inside function, which is 2x take away 14. Plus, same thing with this one, 1/2. Reduce the power by 1 and differentiate by the inside function. By the way, that's a 14, it's just I wrote it badly. And we get that. And all I'm going to do in this line is try a little bit to make it prettier. Now, if you do a half times this, you get 7, you get, I didn't do that mistake. I'll do it over here. So, C dashed is equal to 1 plus 1/2 times 2x take away 14 all over the square root of this guy. Plus 1/2 2x take away 14 over a different ugly square root. Yeah. Can I do a little bit more to that? I guess I could. Let's call that x take away 7 over this ugly square root. And also another x minus 7, but over a different ugly square root. Now we can tell, I mean, just looking at that, would you agree that there's no way I'm going to solve that algebraically? I can't do that. I mean, at least not easily. So I am going to go and use Desmos. And this time, things should hopefully come out a little bit nicer. I have a 1 plus a square root. No, I don't. I have an x take away 7 divided by a square root. That's better. And it's x squared take away 14x plus 58. I'm wondering if I need that bracket. Probably do. Plus an x minus 7 again. Divided by a square root. And I'm going to do an x squared minus 14x plus 65. And I don't like the way this looks in case order calculation kicks in. So let's get rid of, there, looks nicer, great. Now we are trying to find when is this thing here, which is the derivative 0. So what I'm looking for, oh, that's a, well, you get what you get. Can you see it? 5.
No,
Oh, have I been doing that? Sorry, everyone. You're meant to tell me we can't see this. Right. Well, you're just getting the gist of it then. Here is the derivative function in all its glory, right? Written in the same way. We are trying to find out when the derivative is 0. That means in, oh, come on. What did I do there?
Click double back button.
What is that? Where's that listing here?
It's right in the, no, right in the middle of the like where you can type up a little bit
This thing.
right there. Yeah.
Oh, thank goodness. I learned someday. Right. So I must have hit that by accident. Okay, so here is our derivative, all of that. And we want to know when it's 0, means where does it cross the x-axis? Can you see it crosses there at 5? Thereabouts. So we know that x should be 5. And now if I return back to the written work on the whiteboard, let's see if that makes sense. Well, can you imagine what you were going to do is you're going to make this guy here 5 miles. And then that means what? The other 2 miles is where you split. Now, it depends on what the question then asks. If the question said, what should x be? That is your answer. If the question had been, what's the total cable? Wouldn't you plug x equals 5 into this ugly expression here? And I'm not going to do that because it would take me too long, but can we pretend the answer is 17.1? Just made up number. But you can